Hi there, and welcome to insideQuantum, the podcast telling the human stories behind the latest developments in quantum technologies. I'm Dr. Stephen Thompson, and as usual, I'll be your host for this episode. In previous episodes, we've talked a bit about the theory behind quantum technologies and concepts like error correction and learning theory. But what are we actually applying these theories to? In order for them to be useful, we need to apply them to something in the real world, and that's what we're going to talk about in this episode. It's a pleasure to be joined today by Dr. Elliot Bentine, a senior postdoctoral researcher at the University of Oxford who works on ultracold atomic gases, and in his spare time is also a programmer and video game developer. Elliot, thank you so much for joining us here today.
Very nice to be here. Thank you for having me.
So before we get to the video games, which I'm sure people are desperate to hear more about, let's first talk a bit about your career journey to this point, and let's go right back to the start and ask what first got you interested in quantum physics?
I think when I was very, very young, the backstory is my grandfather, who I had a lot of respect for, had basically been a very successful comedian in the UK, and he was quite famous in his day in sort of show business. He was called sort of Michael Bentine. He was a member of the Goons, which was a sort of famous sort of British comedy group back in the kind of 50s and 60s. But he'd actually originally wanted to go into physics, and he'd wanted to do that. And then I think that plan sort of got disrupted when the war had happened, and he'd not been able to go into university. But he always sort of maintained that passion through life, and he had a lot of kind of physics textbooks. He had things like sort of Einstein's relativity and kind of electronics books and things like that in his library. And I think, one of my kind of early memories when I was young was sort of going into his study and kind of looking at these books. And I think in a way, I sort of respected him. He died when I was very young, when I was about 5 or so. So I only have kind of some memories of him, very fond memories. But then in a way, I guess I felt that as I sort of read those books in his study, I kind of got to learn him a bit more that way, and kind of, saw another side to him that was possibly less well known. And so, yeah, he sort of had all these books on physics, and I think that's what kind of really kindled my interests in it. He very much enjoyed making things as well, and I think I have a lot of fond memories of him when I was very, very young, watching him kind of making things. I think originally he'd used that in comedy for making lots of different props and things like that, but he was very keen into sort of making all these cool contraptions and things, and that sort of inspired my interests when I was younger. And then, from that, it sort of carried on. So when I was much younger, I'd made sort of dangerous things in the garden. We made a sort of potato gun, which was terrifying, actually. We used to sort of fire kind of spears across the garden, basically. It used sort of compressed air. We'd pump it up to about sort of 200 psi or so, and it could sort of fire. We had a sort of dowel that we tied a throwing knife to the end of it, and we could fire that 30 feet and send it sort of through a sort of that sort of 3-inch thick sort of wooden construction timber board. Wow. It was good fun.
So you were destined to be an experimental physicist from a young age then?
Yeah. I was very lucky in that we had that stuff available as well. So my dad works as a handyman, and so he has a lot of tools around. He's had a kind of workshop and effectively a space and a way to make things, and he'd make a lot of these things with me as well. And I think that definitely got me into it. And then I think the other thing which sort of helped was being into video games at a young age, because I think that's actually how I originally sort of got into programming, which has been very, very useful, obviously throughout physics. Whether it's for sort of doing experimental controls to kind of write timing systems and things like that we use for these experiments, or whether it's for for instance, simulating some of the physical phenomena that we have to look at, which is, what we'll talk about a bit later as well, sort of how some of that video game technology has made it into our research.
So you acquired all the skills from these various different sort of childhood and experiences in your youth, and then was physics an obvious way that you could apply these and explore these skills in more detail?
So I think it's definitely, I did also like the aspect of physics, which I think most physicists will say, which is kind of, wanting to know how the universe works and trying to understand a bit better the universe around us. But I think also for me, it was very much skills based, in that I did like doing these things. They were kind of hobbies as much as they were, about personal development in terms of learning how to do things and wanting to do cool things with it. And then physics just seemed like a very natural choice, because to be honest, when I got to the end of undergrad, if I'm honest, I hadn't really enjoyed undergrad physics as much as I thought I would. And then by the end of undergrad, I was pretty confident that I would be leaving physics. But then I went, in fourth year, I basically went and did a project in the group where I am now with Chris Foote. And basically, I really enjoyed the research. I hadn't enjoyed the undergraduate teaching as much. I think probably because it didn't really play to those skills as much. And then once I started doing an undergraduate project, it was much more about kind of programming or making things, or that was kind of much more in my comfort zone, and also the things that I enjoyed a lot more. And so I thought, well, if this is what research is, and this is what physics is, and physics is going to let me kind of play with all these cool things, then I should give that a go. And so I went from there into then doing the PhD, and then since then, I guess the toys have gotten more expensive and more complicated. That's kind of how I've ended up where I am, I think.
It's interesting that the undergrad degree almost put you off physics. I think I've heard quite a few people say that the research experience of physics is quite different to the undergrad learning experience, and that it can be a difficult jump. It can be something quite difficult to adjust to when you're sort of thrown into research, and suddenly the questions don't have nice, neat textbook answers, and sometimes the questions are not even particularly well defined in the first place. Finding the question, I guess, is the first step of research, as opposed to the undergrad experience where normally what the question is, the task is to find the answer.
I think for me it was fortunate in that I went from liking undergraduate physics less to liking postgraduate physics more. But I'm fully aware that there are many people where that's the other way around. They've basically gone from loving undergraduate physics and loving the way physics is presented there to then absolutely hating research. In a way, it must be a shortcoming of basically the undergraduate physics course is not preparing people properly for what research is. And I think, or at least I hope, I know there was this push recently to move to this kind of CDT model, where the way it used to be is that you'd go from your undergrad and then you'd basically get plunged into the deep end of the PhD project. And I think now they try and encourage people to do something that's more like you do your undergraduate and then you do effectively like a sort of year master's project where you can test the waters of research, you get a feel for the group and sort of what the research will be like. And then there's still time at the end of that to effectively make a change, or change group or change project, or decide altogether that you don't want to do a PhD, because I think it isn't something that everyone will enjoy, basically, and people should be able to leave if they don't like it and also still get something for their efforts so far.
Yeah, absolutely. In fact, I came through a CDT. That's where I got my PhD. And it's something I've always been curious about, is to see after, 5 years, 10 years, how does that compare to the more traditional PhDs? Where are people? Are people in research? Are people in industry? Are they still using these skills, or have they gone into a completely different field? I think it would be really interesting to see after some time has passed, what proportion of people in academia came through CDTs, and is it any higher than from the traditional model? But I guess probably not enough time has passed since CDTs became a thing to really answer that question.
I wonder if there's a sort of, because also the other thing is like the whole purpose of PhDs shouldn't necessarily be to produce academics as well. I think if we're going to assess sort of how successful that is, we need to kind of figure out, I think probably the answer is should do people enjoy doing it that way more than they used to enjoy the other way? Maybe some people end up just going into industry afterwards, and that's a perfectly valid route as well.
This is true. In fact, the CDT I was part of had a very strong focus on industrial placements and giving people the opportunity to get some experience outside of academia in a variety of different companies, and just explore your options. You could take a few months of just, you could put your PhD on pause essentially for a few months, go work for a patent lawyer, go work for a technology company, go work for anything that you liked, and then just see nice. what worked for you. Yeah, it was an interesting scheme. I have to admit, I didn't really take advantage of that myself at the time.
Another area where I feel that it should be easier to try out when you're doing a PhD would be something like policy, because obviously I don't know. I feel at the moment that scientists are quite underrepresented in policy-making decisions. I think, isn't there some statistic about the number of members of parliament in the UK who actually hold like a a science A level. I think it's something like 4 MPs or something like that. It's just
Oh
like,
wow, it's really that low.
I can't remember what the exact number is, but I do remember reading it and thinking like, wow, that's actually quite frightening. And I guess especially with things like academia, people always say it's kind of a one-way door as well. That like if you sort of get off the train at any point, at any point in the journey, that it'll sort of leave without you. I don't actually think that that's true. I think these days there's a lot more ability to go back and forth between these things.
I certainly get that impression. Yeah.
Yeah, I'd be interested to see if there's a better way to get people in PhD programs to actually take part in sort of a policy making processes, things like that.
Yeah, I think a large part of that also is knowing the options that are available to you. And I think as time goes on, we're more aware that a PhD is not like a death sentence to do research forever. You can leave and do different things, and even within a PhD, I guess, or within a research career, you still have quite some freedom to change fields and experiment a bit, which I think we'll talk about a bit later when we get on to some of your work. So, okay, we've talked there about different career options. So let me also ask you, if you had not gone down the research route and you were not a postdoctoral researcher, what do you think you would have done instead?
I genuinely don't know, to be honest. I probably would have gone into programming, just based on the fact that, so in my undergrad, I'd done some sort of internships at software companies. I like programming a lot. I think, probably I would have gone down something like enterprise programming. I had sort of friends and contacts, particularly from the open source community and various projects I'd been in when I was back in school, who went on to go and take up probably much better paid programming jobs, and they seem to work much healthier hours than we do in research. So yeah, maybe I would have done that.
Okay, so can you tell us perhaps a little bit about the field that you work in? So you're an experimental physicist, the first experimental physicist who we've had on the podcast, and you work in the field of ultracold quantum gases. Can you tell us a bit about what are ultracold atoms and why are they interesting? What kind of challenges can they be used to address?
Okay, so ultracold atoms, obviously the most obvious thing in the name is the cold temperature. And I guess firstly we should ask, why do we need to have things that are so cold in the first place? The kind of physics that we're interested in is predominantly quantum mechanics. And the reason that we want to go so cold is basically that, in quantum mechanics, you have this quantization of the energy levels of the system. And obviously that's a kind of true behavior of the universe all around us. It's just that normally the splittings of those energy levels are so small that at the energy scales we're used to in the classical world, we can't resolve them. It's like the graduations on a ruler are too fine for us to see. So what we do is we make the temperatures much colder, and in doing so, what we're really doing is reducing the energies in the system, the kind of characteristic energies that are involved, until our system then reaches a state where those energies are comparable to the splittings, so that we can begin to make out the types of changes in behavior that occur when something is dictated by quantum mechanics rather than by classical physics.
So how cold are we talking here? How cold is ultra cold?
So ultimately we're going down to sort of, depending on the type of experiment you want to do, maybe 10 nanokelvin or colder. It's quite hard to picture what these temperature scales are. I think probably, if you think of what the hottest thing is, probably most people would say the sun, and the sun has a surface temperature of about 6,000 Kelvin, and then room temperature is 300 Kelvin or so. So really, to go from room temperature to the sun, you're really only going up kind of like 1 or 2 orders of magnitude. So when we then say we're working at 10 to the minus 8 Kelvin and room temperature is 10 to the 2 Kelvin, so you go from room temperature to the sun, that's 2 orders of magnitude. And then, we're going kind of like 10 orders of magnitude colder. So that puts into account really just how cold we have to go. I think if you ask most people, what is the coldest thing that you can imagine? I think almost all of them will probably say, well, I think a lot of people would say liquid nitrogen. That's like, 70 Kelvin, I think. And then liquid helium, which is like 4 Kelvin. And then people might say like, outer space or so. And outer space is, what is it? A millikelvin, I think.
Isn't it 2.73?
2.7. Okay, so that's hot, really hot. That's basically a sort of summer holiday. So we're substantially colder. And then the question is, so that's sort of the why. You want to get cold enough so that you're able to make out these laws of quantum mechanics, and then you can push and you can probe your system, and you can watch how it responds. And that's kind of the general idea behind sort of quantum simulation, is that you're making your system look like something else, dominated by quantum mechanics, and then you're sort of seeing how it would react to solve a problem that would be intractable otherwise. You couldn't necessarily sit down and work out the theory for it. The other reason you want to go very cold is because when you're very, very cold, your environment is very quiet. And so when you're very, very cold and you have these kind of systems dictated by quantum mechanics, you can then make very accurate measurements of things, be it time or magnetic fields. And so then that's also the whole field of quantum sensing as well comes out of that. So that's the kind of why. And then the how, we kind of use... There are predominantly sort of two techniques that are used to get down to very, very cold temperatures. The first one is laser cooling, which is almost certainly the first stage that people use to get to those temperatures. And that might sound like it's slightly paradoxical, because most people would associate lasers with heating things up. It's a stream of energy. You have this kind of bombardment of photons, and each photon's carrying some energy with it. So you'd expect that might cause your thing to heat up. But in laser cooling, you are using the fact that each of those photons carries momentum as well. And so you arrange your system so that each atom is absorbing photons traveling in a direction opposite to it. So actually that absorption of the photons acts to slow the atom down. As it sort of takes that momentum from the photon, it's decreasing the velocity of the atom. And so you can use that to kind of reduce the temperatures of your atoms. But you can only use laser cooling to go so far. But laser cooling is very effective, and it is more or less the starting point for all of these experiments. And then the way you go down to the absolute coldest temperatures tends to be, in most labs, a method called evaporative cooling. And what you're doing in evaporative cooling is very similar to how you would cool down a cup of coffee. When you have your cup of coffee, you blow on the top of it, for instance, and by blowing on it, you're removing the atoms with the highest energy that are able to sort of momentarily break out of the surface of the coffee, and your breath then sweeps them away. And by removing the atoms which have greater than average energy, the atoms that remain must then have less average energy than the average energy of your entire atoms did beforehand. And so by doing this process again and again, kind of cutting away the sort of highest energy atoms and letting the remaining atoms rethermalize, you can basically act to sort of reduce the temperature of your system. And so that's how we can take our atoms all the way down to kind of tens of nanokelvin or so.
So you're cooling atoms down to temperatures colder than space, I guess temperatures that are probably not found naturally anywhere in the universe as far as we know.
Yeah.
and you're doing this so that you can study this kind of very quantum regime where there's no thermal fluctuations, nothing else. There's only quantum mechanics is the only game in town, and you have this very kind of clean system where you can study sorts of quantum phenomena that are very difficult to access in other ways. Is that a fair summary?
Yeah, exactly.
Okay, interesting. And you mentioned there are a couple of different applications. So previous episodes of this podcast, we've talked about quantum computing and how you can use certain experimental setups to act as quantum computers. But you mentioned a very different application in there of quantum sensing. What's the advantage of having quantum mechanics in a measurement device?
So I guess there's two separate aspects to it. One is that when you have atoms and you're looking at the level of individual atoms, quantum mechanics is present in almost every part of what dictates what you can do with those atoms. For instance, quantum mechanics will be present in determining the energy level structure that then dictates how you can interact with the atom, whether you can use magnetic fields to perturb the atom or optical fields, what kinds of fields you can use, whether the different polarizations or frequencies they are, etc. So I think one part of it is that the atoms have a very high degree of sensitivity to external fields, depending on whichever state they may be. Because you have an ability to measure, for instance, the energy separation between two energy levels to a very high degree of precision, if an external field were to change that energy level separation, it would allow you to basically determine to a high degree of accuracy what that external field is. Because effectively you have a way to, if you can very accurately measure what this separation is, you can then look for very small deviations in it. And therefore that gives you a very, very precise ability to determine what the external field is.
I see. So because these atoms are so cold and so well controlled, you can characterize them really well. You know in quite a lot of detail all the properties of these atoms, and that lets you watch for when these properties are changed. And you can measure these changes, and this is why ultracold quantum matter can be used for very precise sensors then?
Well, yes, so that's kind of one part of the story, and then the other part is that there are several kind of specifically quantum mechanic effects that you can use to also perform precision measurements, in a slightly different way. So one is almost like the precision and control that you have over these systems to then measure these energy levels very precisely, and the other way is that you can use, so for instance, you can use quantum effects like interference. You can take an atom, you can put it into a superposition, and then when your two different states are then affected differently by some external field, you separate your two states, some external field changes the energy of these two states in a different way. You sort of let time do its thing for a little while, and then you bring the states back together. That then produces a kind of differential signal that you can measure. So you're looking for, at an interference signal that you can measure very precisely.
I see. So by comparing these two different atoms, these two different copies of your system, by comparing them and by, I guess, physically moving them on top of each other and looking for interference effects, this gives you another way to really accurately probe any changes that have been made.
So I guess I should rephrase it slightly in that it doesn't necessarily have to be a spatial separation. It depends what kind of field you're looking for. So for instance, if you were wanting to measure a magnetic field, you may actually want to keep the two different sort of states of your interferometer at the same location, but just have one of them sensitive to the magnetic field and one of them not. So that then when the magnetic field is applied, you get some energy splitting between them, then you bring them back together and you look at your differential signal. If you wanted to measure, say like rotation, for instance, then you'd need to find a way of separating your states in space so that they could, maybe you send them around a ring in two different directions so that when your ring is rotating, one of them has traveled further than the other has traveled. And then that would be the path length difference that produces a signal in your interferometer.
So you mentioned there the word interferometer a couple of times. So that's a device that uses interference to make measurements. Can you give us any examples of use cases of interferometers, either historical uses or more modern cutting edge uses?
So I think probably the most well-known interferometer is the Michelson-Morley interferometer historically. It's a very simple device. You have, effectively a beam comes in from the bottom. You have a beam splitter. You send your beams down two directions, your sort of two different paths, and you reflect them off mirrors, and then you bring them back to the beam splitter, and then you send them off to a detector. And then what I think Michelson-Morley were trying to measure was whether or not there was a sort of ether, like was there a stuff that we were moving through, some sort of absolute reference frame of the universe, so that then if your interferometer was moving, you might see one of the lengths kind of change compared to the other one, but they didn't see that. so then that was, I guess, quite an important proof of relativity, the idea that all inertial frames were equivalent to each other.
So the idea of it is you split a beam of light in two, you let the two paths do their thing, you recombine them, and then you're looking to see, is there some difference between the two paths, and that tells you that they've been affected differently. And in the case of this experiment, that would tell them something about what the universe was made of, and if there was an ether.
Yeah, and so I think it's probably worth mentioning that one of the projects that I was more recently working on is Aeon, which is this UK attempt to build a sort of large-scale atom interferometer that can look for things like gravitational waves and dark matter. And then what Aeon wants to do, Aeon is not a traditional atom interferometer in the normal sense. It's actually more equivalent to using the precision measurement techniques of optical clocks as a way to time how long it takes for a laser pulse to travel between two test masses. The test masses are individual atomic clouds that are freely falling. Mm-hmm. So it does use interferometry, but it's slightly different to the normal case. What it means is that you can use the techniques developed for measuring time very precisely to now measure a length very precisely. And then if a gravitational wave travels through your device, it causes a very slight fluctuation in this distance. And so what you're really doing then is using the timing of these pulses to precisely measure the small contractions of that space so that you can then measure the passing of your gravitational wave going through the device.
I see. Okay, so the idea then is you have these two clouds of ultracold atoms that are separated in space. You're using lasers to measure very precisely the separation of these two things, and if a gravitational wave comes by, that changes the separation. I guess the two clouds will wobble in space, and
Yeah,
you can
they'll move sort of
detect
up and
this.
down slightly, for instance, and so you look at that kind of very subtle contraction of their separation.
Right. And then, okay, that's interesting, because if I think about gravitational wave detectors like LIGO or Virgo, these reasonably well known big experiments. These are big experiments, right? These are what, tens, hundreds of kilometers long. These are very, very large scale experiments. What kind of size of an experiment do you need to do this with an atom interferometer? Do you also need to have these clouds of ultracold atoms separated by tens of kilometers, or is this something you can do in a single room in a lab?
So the kind of threshold length, I believe, where you can start to look at gravitational waves is when it reaches around about 100 meters or so. I believe it's because your kind of characteristic wavelength for a matter is actually much smaller than that for light. And so as a result, you need a much smaller length scale to observe the same change.
Right, so you don't need an experiment to be quite as large as these light-based interferometers then. In principle, these atom ones can be much more compact.
But it's interesting, the comparisons between the two types of technology are actually not necessarily as straightforward. So basically, each type of device has a sensitivity that falls in a different frequency range. And so Aeon and other kind of atom interferometers would be sensitive to what's called the mid-band frequency. It's worth also mentioning there is a project in the US, MAGIS, which is sort of leading the way on much of this, which Aeon is kind of collaborating with.
I see. So these are complementary to the existing gravitational wave systems. They're not a replacement.
Yeah, exactly. I think obviously that works out nicely in that it feels like everyone can win.
Yeah. Okay, nice. That covers some of the cold atoms aspects of what you work on. But at the top of the episode, we mentioned a bit about video games. We mentioned this a few times. So let's come back to this now. Outside of your day job as a postdoc, you're also a video game developer. How did this come about?
Well,
how do you have the time?
I guess the thing is, it is truly a hobby. I mean, it's something that I enjoy doing very greatly. So, it's quite nice to do it in an evening. There's a very creative part to video game development as well, particularly things like graphics programming, because and also quite a lot of overlap, to be honest, with atomic and laser physics. Atomic and laser physics is all about the interaction of atoms with light and matter with light, and you have to think a lot about how that sometimes gives rise to different optical properties as well. When you do graphics programming, what you're really writing is ways to determine the color of pixels on the screen based on things like, the normal of some mesh, the direction it's facing, the way the light's illuminating it, what it's made of. And obviously these are all kind of, what you're really doing is finding ways to approximate how that should look, because the real world around us, and the colors we see and the types of phenomena we observe, they're made up of a very great number of different aspects. So if you think of, for instance, water, the sun reflecting off the sea, there's a lot going on there. There's things like subscattering of the sun's rays hit the water, they go under the water a bit. There's then sort of random directional scattering, and then some of it comes back up. There's also the fact that different polarizations will reflect differently. You then have the kind of rippling surface of the water. So, some parts will be bright, some parts will be dark. You might have things like foam and surf on the surface of the water. Maybe now your water isn't water, maybe it's oil. And so you have a sort of iridescence, a kind of, colorful rainbow that you see on the edge of the oil. All of these things, if you kind of think of them even at a sort of undergraduate level of physics, you might be able to work out where some of these individual things come from. And so when you're writing graphic shaders, you're kind of adding more and more of these approximations to better approximate the behavior that you want to reproduce, but to do it at a really fast frame rate. Because when you're doing graphics programming, it all comes down to the fact that ultimately your programs have to be fast because they need to render to the screen multiple times a second. You have to run these programs sometimes for millions of pixels, and they need to be done, in a way that you get that nice, smooth sort of 120 frames per second gaming that people expect these days. So there is a lot of overlap in the sense that there's physics you have to think about sometimes. There's a lot of mathematics as well. There's also kind of high performance programming techniques. And personally, I enjoyed it a lot. So I was sort of doing that just for fun anyway. And And then I joined the kind of Oxford Indies. There's a kind of group of independent developers in Oxford. And so I joined them and sort of went along and kind of met them for a few different lunches and things. And Tim Watts, who I've become very good friends with, basically said to me like, "Oh, this particular one you're working on, which is a sort of set of shaders to render a 3D object to look as if it's a 2D sprite. It's just like a very stylized graphical style that happens to be quite popular at the moment." And he sort of said, "Oh, you should look into selling that." And so he convinced me to sort of pursue putting it onto the Unity asset store. So Unity is a big game engine. I think something like 70% of all games are now made in Unity. So it's got a very large number of users, extremely popular resource, and it has an asset store, so you can basically upload things and then sell them. Unity obviously takes some royalty on that, but it has a great many users, and so he sort of convinced me to do that. And I'm very glad I did. So it's sort of, selling quite well.
It's interesting that you mentioned the performance aspects, actually, because in science, I guess that's not something we really have to contend with in the same way. I suppose that you want your simulations to run in a reasonable time frame, or if you have access to some kind of national cluster computer, maybe you have a few 100,000 hours and you've got to get your code to run in those few 100,000 hours. But that's different to video games where you've got, something like 33 milliseconds to target a playable frame rate, something like this. So like,
yeah, even less these now, because people get incredibly fussy.
Yeah, so I guess there's some really different pressures and different things you have to think about when coding a game. When you're talking about performance, it's really how quickly can you draw this frame and get it on screen, as opposed to how accurately can I compute this quantum phenomenon. There's some trade-off between how realistic do I want it versus how long is it going to take to render this scene. Okay, so we've talked a bit about your interest in games as well as your interest in science, but you've also managed to combine these two. Can you tell us a bit about how game engines can be used to demonstrate and to teach some aspects of quantum physics?
I have a lot of respect for the kinds of technologies that go into modern game engines. So a lot of these are now very, very well engineered pieces of software that hopefully isn't too surprising, because they're worked on by sort of thousands of people at a time now. And the kinds of tasks they have to do are very computationally intense. There's the graphics rendering side, which I've said a little bit about, but there's also usually a whole host of other calculations that are going on under the surface to sort of determine how the game should play. And so one of the patterns which has become particularly popular in video games recently is a particular architectural pattern called entity component system. And so we've kind of used this particular approach to great effect in some software that we've written recently for sort of doing simulations in ultracold atoms. Ultimately, we'd like to use this for outreach as well as for research, but our main reason for writing this software was actually for the research side. So the reasons we decided to use this particular pattern is because it's really highly performant. As I say, one thing is that you can write this code and it can run in parallel very easily. And it's also very modular and kind of easy to extend and easy to test it. And obviously, if we're writing code that's used for research, it's very important that we know that it gives the right answers. Mm-hmm. And so I put a lot of value in us being able to write tests very easily to verify that individual core components of this software are doing what we would like them to do. And so we wrote this code called AtomECS. So I did this in collaboration with Dr. Tiffany Hart, who's over in Cambridge. And we had students that we worked with as well for this. And we basically used this to simulate a variety of different cold atom systems now. So we were sort of building this up to be a kind of general purpose cold atoms research code. So we do it for things like simulating the laser cooling processes for the atom sources in Aeon, also things for simulating the transport of cold atoms in optical traps, for simulating the evaporative cooling of atoms. So there's a whole host of problems that we can look at using this code. One of the very nice things is that because we are using a pattern from video game development, we're also then very easily to integrate it into sort of existing video game software sort of ecosystems. And what that's given us for free basically is the ability to then use the rendering software from video games to make very nice demonstrations of this physics. And even cooler, we can actually compile it for web as well. So hopefully we can add a link to at the end of the podcast to one such demo, which is sort of showing how the laser cooling source works for Aeon. So it's a demo that shows basically an oven which is emitting a bunch of strontium atoms, and then those atoms interact with some sort of cross-diagonal laser cooling beams. The atoms are slowed down, and then a third beam kind of pushes them out of the chamber. And what I would really like to do is see multiple of these demos made. Ideally, I'd go around and collect all the CAD files from different PIs and see which of them want a sort of demo of their apparatus made. Because I think it would be a really good opportunity for sort of teaching and outreach. I think it would give hopefully people a bit more of a kind of intuitive feel for what's going on in these experiments. Because I think when someone looks at these kind of cold atom apparatuses, they can be quite daunting. They're large pieces of vacuum apparatus with lots of sort of windows, lots of beams going everywhere, and it can be quite hard at first to disentangle what each of those beams is doing. But hopefully, if you've got some demo that you could, change some sliders to sort of change the detunings or turn beams on and off, then, you could give that simulation to people and they'd be able to sort of play around with it and find out what's going on and sort of look under the hood a little bit. So that's a bit of the dream there, is that we can use this research quality code also for doing outreach, because we can cross-compile it against the sort of video game rendering libraries that are out there, and then, basically compile it for WebAssembly and put it up. So, yeah.
So physicists and other research scientists have something that they can learn from video game developers then, in terms of how do you write good, fast code that can be tested well, and that as a bonus also allows you to have some kind of intuitive view into the physical system that you're simulating.
I think so, but I think, to be honest, and without being too rude to physicists, I think a lot of physicists could learn a lot about code full stop. I think academia is famously bad when it comes to keeping up with modern programming practices. I'm very pleased to see that things like Git and version control are now more widely used in academia. But even until recently, I know of research groups who still just take each version of the code and put it in a new folder labeled version 1_new or something like that. And obviously that leads to sort of errors, and ultimately will lead to sort of incorrect conclusions that then go on and get, sort of appear in papers. So I think when you compare that to sort of the sort of whole software industry that's had to figure out ways of solving these problems, and also to work collaborative as well. They've got very good collaborative tools that are quite well suited to doing sort of programming in any team, not just theirs, but also in the kind of teams you have in research. Then it seems a shame not to use those tools.
It's a good point. There's a serious point in there about reproducibility of your code and your numerics, because if you can't reproduce the conclusions of an earlier study, then that's a really big problem. And you're right that being able to use these sorts of best practices, I guess, from an industry that really requires them, if we can borrow these best practices and use them also in research, then that does really benefit us as well. Have you seen much interest from the wider community in adopting these tools, or have groups that have long-standing codes, have they been quite content to keep their closed code and work with that, or have they showed some interest in becoming a part of this project?
So I think we now have had kind of pull requests accepted from quite a few different groups now. I think it's quite hard to estimate how many different groups have used it, because often people on GitHub will use a handle that doesn't necessarily correspond to their real name. So it can be quite hard to track and work out, who different contributors are actually, like which groups they're coming from. But we know, I know of at least 5 or 6 different groups now who have used it for simulating different things. We'd still like to improve it a bit more and make it so that it's really, really user friendly, so that people can quickly take it and use it in their projects.
Okay, great. So there's one question that I like to ask all guests on this podcast, and that's to do with the gender balance in this field. So you've talked a bit about your experience both in physics and also in programming and more kind of computer science based fields. These are both fields that in recent history, let's say, have been very, very male dominated. Is this something that you've seen changing over the years of your career? Have you seen these fields become more equal, or noticed any appetite, any kind of momentum towards making these fields more equal? Any kind of positive changes in these fields?
there's obviously a lot of issues that are still very entrenched in physics. Quite often I see, all male panels at conferences, for instance. It's a terrible balance in physics. And I think that there was a recent analysis maybe 2 years ago that said that physics is actually is actually sort of one of the only STEM subjects that's going backwards, and where the divide is actually getting worse.
Oh, really? I hadn't heard about this.
That is kind of possibly, well, I hope that's outdated now. I don't really know how to fix it. I mean, my own personal view is that I've sort of largely given up on academia just as an entire sort of as an entire culture, basically. I mean, that's somewhat my reasons for basically leaving physics in the near future. Like, it's very reluctant to change. I don't have the answers of how to fix it, and personally, I'm really tired of it, and I just sort of feel I just can't really carry on working in it. So yeah, I've sort of taken the decision to leave academia, basically, and try and do research a different way. That's not what I was thinking of doing a few years ago, but I don't know. I feel at some point, if I stay, I'm just sort of enabling the culture. If the culture exists as long as there are people around to sustain it, and I don't know. Gender imbalance is obviously one important thing. It's just very white male dominated at the moment. There's all kinds of groups who are very poorly represented in physics, and I don't know how to fix that or change that. So some people will claim, for instance, that's down to effectively access needs to be made sort of earlier on in people's careers to get them into physics. But also, I've seen enough of people having horrible times within academia and within physics to feel a little bit of well, if it is broken and it's not going to give people opportunities even once they're actually in it, then am I actually doing something of a disservice, encouraging people to just throw themselves into this completely broken system? Yeah, I don't know.
That's an interesting point, I guess. Rather than trying to fix the system from within, your preferred approach then is just abandon that system and create a new and better one in the first place that doesn't have these entrenched sort of years and years of biases and problems that are built up over a very long period of time.
I would like to create a system like that. As in, I would like to create a new place where you could do research that wouldn't have the sort of problems of academia. I wonder to what extent the private sector and kind of industries that are basically very physics heavy in the private sector, have they found out ways and solutions for fixing this problem? I know some of them haven't, because some of those companies are also still very white male dominated. But I hope somewhere there are companies that have. Yeah.
Well, if there are, then I hope the rest of industry and research can learn from them and adopt some of their practices and make physics a bit more welcoming to people from all backgrounds, really, from all walks of society, and make things a bit more equal and a bit more diverse. As a final question to end on, then, if you could go back in time and give yourself one piece of advice, what would it be?
I think probably the most important thing that I've always tried to encourage other people to do during the PhD is to basically, I try and encourage people to just learn as many different skills as possible and to kind of work on that level of personal development. Like, on the one hand, it should be because you enjoy doing those things, follow your interests and kind of work on the things which you are enthusiastic about. But I think it's sort of go out of your comfort zones a bit, and try and learn as many different things as you can, because you don't really know necessarily when things are going to be useful. The sort of slightly eclectic bunch of skills that I picked up over the various years, ranging from things like graphics programming, which has become useful in physics, and also kind of game programming, which has now also become useful in physics as well. To all these other kind of things, so for instance with the physics, in doing cold atoms, you learn, and experimental cold atoms, you learn a lot about different computer-aided design things, or how to manufacture things, or you learn about optics and lasers, and at the time you're kind of learning them because you need to learn them for your experiment. But those are actually very, very useful and valuable skills in and of themselves. So one of the projects that I'm now working on with a postdoc from cardiovascular medicine called Dr. Winnick Lapidaire is a sort of imaging device for cardiovascular medicine. And that's obviously is completely different to the quantum physics that I'm more usually used to. But really, what it draws on is that whole experience of working with lasers and optics and designing those types of systems for imaging cold atoms. But now, instead, I'm trying to image, for instance, small blood vessels, instead for kind of medical care rather than for doing physics. So, yeah, I guess if I was gonna say some advice, I would just say learn sort of as many things as you can and learn them because you're interested in them, and just kind of follow your passions that way.
Okay,
Yeah.
So learn as much as you can. You never know when it could be useful or what kinds of unanticipated opportunities could come your way because of it.
Yeah.
Okay. I think that's a great place to end. So if our audience wants to learn a bit more about you or check out some of these simulations that you've mentioned, where can they find you on the internet?
So on Twitter, I'm Dr Bentine. So DrBentine.
Okay, great. We'll make sure to leave a link to your Twitter profile and possibly, I think, also your GitHub repository and various other links, so our audience can always check out some of the things that you've talked about here today. Okay, great. Well, thank you very much, Dr. Elliot Bentine, for your time today.
Thanks very much for having me.
Thanks also to the Unitary Fund for supporting this podcast. If you've enjoyed today's episode, please consider liking, sharing, and subscribing wherever you like to listen to your podcasts. It really helps us to get our guest stories out to as wide an audience as possible. I hope you'll join us again for our next episode, and until then, this has been Inside Quantum. I've been Dr. Stephen Thompson, and thank you very much for listening. Goodbye.
Bye.